we are considering how do you represent these m possible signals. So we can represent that as Si of t. It is the symbols combination from I is equal to 1 to m, or you can say that it is the complete signal S of t. It is the, because these bits you have derived from an analog signal S of t. So this are m of t. This m of t, when it is converted into bit streams, you will get bits. From there, what you are doing, combining bits, you are forming these symbols. Total all the symbols, if you combine together, you will get back your m of t. So therefore, we will be representing the difference between m of t and Si of t is that this Si of t is the modulated signal we are going to consider. Okay, this modulated signal having different possible phases when they are added. So I is equal to 1 to m x I of t. Sum it up all the symbol signals. So here, which implies that the signals x1 of t which is there, sorry, s1 of t, this you take it as s1, s1 of t, s2 of t, etc., s3 of t, etc., xm of t are all the possible signals. Either you can go for x of t or you can go for s of t. It is one and the same. X of t, how did we got? What is x of t? As per the block diagrams which we have discussed in previous class. S of t, it is equal to S of t, it is equal to, sorry, x of t is equal to S of t. How you derive, you got this S of x of t. What is the white, where the white Gaussian noise you are adding?
SA of t.
No, x of t or S of t, modulated signal, when it is, what is modulated signal? How do we represent it?
Si of t, ma'am.
Yes, I of t, yeah.
Yes, ma'am.
Okay, Si of t plus W of t we have considered, right, as x of t.
Yes, ma'am.
Okay, okay, fine. So now this xi of t or Si of t, when we are considering, it may be S1 of t, S2 of t, S3 of t, etc., Sm of t. So this is what the number of symbols we are going to transmit over a channel. So when these channels we are transmitting, these signals when we are transmitting, we are converting these signals, transmitting over channel. We will represent these signals in terms of n orthonormal functions. Means each particular signal, when it is transmitted, it will have some amplitude. That amplitude, it is based on this zero, symbol 0. I may take as an amplitude of 1. The symbol 1, I may take as an amplitude of 2, 3, 4. So these signals, when we are transmitting, we will represent these signals before transmission in terms of n orthonormal basis functions. How do we represent these orthonormal basis functions? Means phi j of t, it is equal to phi 1 of t, comma phi 2 of t, comma etc. phi n of t. So you have m signals. These signals we will be transmitting over the channel by converting into an orthonormal function. How these M signals we are going to convert into an orthonormal functions by multiplying these M signals, that is S1 of t in comma S2 of t etc. up to Sm of t by using the orthogonal functions. Because what is required for the optimization of the communication channel, to optimize the communication channel, the very first need that should be there is that whenever two signals are orthogonal, there should not be an intersection of any two signals. So therefore we will be choosing the ortho basis functions, and these basis functions will be choosing in such a way that every signal will be getting multiplied with one basis function. These basis functions, when they are multiplied with these signals, it is termed to be the linear combination. Okay, this is what the idea, the orthonormal functions. These are the signals, these are the orthonormal functions, because every signal should satisfy orthonormality and orthogonality. So therefore we will be choosing the n basis functions to transmit these m symbols. N basis functions we are going to choose, where n should be lesser than or equal to m. That condition for the basis functions you need to consider. Now ideally any signal before transmission, because that block diagram already you know, ideally any signal uh, x1 of t or x2 of t or x3 of t etc. xn m of t, when they are transmitted over a channel, can be represented as a linear combination of n orthonormal functions. So hence you can represent your signal, ith signal xi of t as what? Xi of t, that is the ith symbol when it is ith signal, that is ith signal. Let us take ith signal. Take ith signal. When you take an ith signal, how do we transmit this ith signal? Means it will have this ith signal will be multiplying with individually the n r basis functions. So first one let me take as phi1 of t, x i2 phi2 of t plus etc. x I n phi n of t into, okay. Now this you can call it as, okay, this xi of t in terms of orthonormal functionality, when you are representing any signal j is equal to 1 to n, what is your actual signal? It is xi j, because j is ranging from 1 to, here j is 1, 2, etc. n. These are representing the basis functions. Fine. So xi of j into phi j of t, this you can call it as equation number 1. Here I is equal to 1, 2, etc. up to m symbols. J is nothing but each signal. How do we represent? Using how many orthonormal functions that will be represented here, representing your signal. See, very simple. Let me consolidate whatever I have explained from the first topic to here. It is, you have the m symbols. Each symbol after modulation you are converting into a signal, discrete signal, which is represented as Si of t. That I stands for M possible symbols. When these symbols, when we are transmitting over a channel, we have to maintain the orthonormality as well as the orthogonality. So since this property has to be satisfied, we are considering n orthogonal basis functions. So whenever these basis functions you are choosing, which is represented as phi j of t, which is phi 1 of t, etc. phi. So those orthonormal basis functions, when they are multiplied with the actual signals S1 of t, S2 of t, S3 of t, your signal over the transmission, over the channel, when it is transmitted, it will give less interference between the signals. So hence, thereby it satisfies the orthogonality and orthonormality. Hence, it is must to convert the signal, incoming signal, into the ortho. So here, if you have the xi of t, this you can take it as x1 of t, x2 of t, x3 of t, etc. All those things. Otherwise, that notes I'll share it. If you have an s1 of t, s2 of t as it is, you can consider. Now this you can call it as equation 1. So whatever this xi of t, which is converted to get transmitted over a channel, it is called as synthesizer. It is also termed to be the transmitter block. If you are considering the equation 1 from above equation, that is equation 1, this xij, what is that? Xij is equal to 0 to t xi of t into phi j of t into dt. What does that mean? What is the signal that you have transmitted? The signal which is getting transmitted over a channel is xi of j into phi j of t. So after transmitting the xi of j, this is a signal vector. This signal vector, how do we calculate? Means it is any symbol, if you take its duration is between 0 to t, xi of t, integrate xi of t with phi j of t into dt. Here I is equal to 1, 2, etc. m, and j is equal to 1, 2, etc. n, where t is symbol duration. Okay. Now the basis functions, when we are using with these signals, one more thing, the basis functions, which are the functions? Phi 1 of t, comma phi 2 of t, etc. Phi n of t. When we are considering, they should be orthonormal. So these are basis functions should be of orthonormal in nature. So therefore, whenever, that is, when you are integrating any normal signals between between the symbol duration, its output should be 1 if I is equal to j and 0 if I is not equal to j. This 1 is represented, this 1 in the function, you can represent that as an unity function, or you can say that it is delta ij. What is this delta ij means? It is knocker delta function. Okay, so therefore you can see here, when I is equal to j. What happens? This above function. This you can call it as equation 1. This you can call it as equation 2. And equation 3 is, 1 minute, xij. Yeah, this is equation 2. And equation 3 is this one. Okay. In equation 3, I is equal to j implies what? 0 to t phi I square of t into dt, which is equal to having a value of 1 and 0 when I is equal to 1, when I is equal to j and I is not equal to j, its value will be 0. This means that basis functions phi1 of t, phi2 of t, etc. phi n of t are orthogonal to each other over the interval 0 to t seconds. Means two orthonormal functions, when you are choosing, both will have different signal periods. So therefore, when you are multiplying with such orthogonal functions, orthonormal functions, your output will be 0. There is no common uniformity between the signals. So now, in order to understand this complete whole concept, let us go for one example. Example, when n is equal to 2, that is number of, first let us understand how these signals we can orthonormal functions. And m, number of symbols as 3, number of message signals, because it is modulated signal. Okay, now you find out xi of t, that is signal. What is j? J is equal to xi of t. How do you calculate? It is the summation of j is equal to 1 to n xij, signal vector, multiply with the basis function what you have chosen, where I will be equal to 1, 2, 3 and j is 1 to 2. Okay, where I is equal to 1 to 3 and j is equal to 1, 2, because n we have chosen as 2 and m as 3. So therefore, you can re-represent this as xi of t as summation from j is equal to 1 to 2 xi of j into 5j of t. At I is equal to 1, how do you represent these signals? What is when I is equal to 1? Xi of t. It will be x1 of t. It is equal to xij. I is what? 1. J is, to start with j. J is 1. So x11 xi, yeah, x11 into phi1 of t plus x 1 2 into phi 2 of t. Is it clear, students? When I is equal to
Yes,
2, I is equal to 2, x2 of t, which is nothing but x, I is 2, so 2, 1, phi 1 of t plus x2 of x2 2 into phi 2 of t. Similarly, because I should range from 1 to 3, when I is equal to 3, x3 of t, it is equal to x of 3 1 phi 3 of t plus, sorry, phi 1 of t into x 3 2 phi 2 of t. What are your observations from here? There are few observations you can conclude from the above equations. x1 of t, x2 of t and x3 of t are totally represented in terms of what? Two orthonormal basis functions are expressed in terms of phi1 of t and phi2 of t. Okay. From here, this is the first observation. Second observation from the above three equations is that the three message vectors three message vectors x1, x2 and x3 can be represented on Euclidean space having two basis functions phi1 and phi2 Euclidean space. And here the third observation, phi1 and phi2, always you should choose they are orthogonal to each other because they must always satisfy the optimal switching or optimal system design. And the fourth observation is that the message vectors, which are the vectors here? What you are representing? x11, x12, x21, x22. They are all the message vectors. Message vectors from which the message vectors x1, x2 and x3 on signal space depends on coordinates. Which are the coordinates? Coordinates are x11, x12, x21, x22, x31, x32. Coordinate values. That is, if you are taking x1 of t, which is equal to x11 phi1 of t plus x12 phi2 of t, then x2 of t, it is equal to x21 of phi1 of t plus x22 phi2 of t, x3 of t, which is x31 phi1 of t plus x32 phi2 of t. Assume, so now you have the coordinates. Which are the coordinates? Assuming coordinate values as, let me take the coordinate values for x11 comma x12 as 3 comma 1 and x21 comma x22 let us take as 1 comma 3. Okay, and here x3 comma 1, x3 comma 2 as equal to 2 comma minus 2. Suppose you are deriving the message vectors x1. x1 is a message vector of x1t. So it is computed as x1, which is equal to x11. What is the value of this x11? 3 into phi1 of t. Or just I'll be writing it is orthonormal basis phi1 of t. or just phi 1 of t. Phi 1 plus, what is your x1 to 1 into phi 2? This is, you can call it as equation 1. x2, similarly the message vector of signal x2 of t, it is equal to, what is the value that we have? x1 phi 1 plus 3 phi 2. x3, the message vector x3 is x31 to phi 1 plus minus 2 into phi 2. How will we represent these signals combined together? So that is illustrated here. We have chosen two orthonormal functions.
Ma'am, page didn't get changed.
Yeah. I have changed it. Two orthonormal basis functions. Here phi 1 and phi 2 both are orthogonal to each other. So now the coordinates, let me write 1, 2, 3. Similarly on the negative side -1, -2, -3. So on positive side +1, +2 and +3. Okay. Now what is x1? x1 is what? x1 is 3 phi 1 plus phi 2. 1 phi 2. So your x1 is 3 here and 1 phi 1. 1 is here, 3 is here. What is this message vector is? It is x1. Because whenever we are going for any message vectors, it will have magnitude and phase. That is the reason why we have chosen this message vector as a combination of the coordinates with basis functions. What is x2? x2 is 1 phi 1 plus 3 phi 2. So 1 phi 1 is 1 and phi 2 is 3. What is this? This is here x2. x3. x3 is, please speak out, 2 phi 1 plus minus 2 phi 2. 2 or 3? Yeah, 2 and minus 2. Now this is minus 2 and this is plus 2. Phi 1 is 2. Phi 2 is minus 2. So this is the point. So we'll take this. This is what? This is here x3. So this is an message vector for 3 signals x1, x2, x3. And this figure illustrates geometric representation of signals. Okay. For what case? Signals for phi 1 and phi 2, that is n is equal to 2 and m is equal to 3. Now, given n elements of vectors xi operating as input, we may use the scheme as shown below to generate xi. How do we generate now xi? Suppose x1, how we are we generating? Message source, message signal or message vector x1, what is the equation that we have chosen to derive this x1? Signal coordinate x11 multiplied with phi 1 plus x12 phi 2 plus x13 phi 3 and so on up to phi n with x1 n. So in general, if you are representing this x1, how do we represent this as equal to xi1 xin into phi 1 of t or phi 2 of t or phi 3 phi j of t. So this is what an signal vector, message signal vector. When it is illustrated through the diagram, x1, xi1, okay, xi1 is equal to, sorry, xij, which is equal to summation from I is equal to 1 to n, xi, xj, xij, phi j of t. So, okay, now it is nothing but similarly xi2 yes, sum it up. So this will give you xi of t. So this is what the transmitter block or synthesizer block. Okay, I'll continue in the next class.